All right, welcome to part 3 here, 8.2 trigonometric ratios. So in this part, we're going to be talking about actually evaluating the trig ratios and getting some decimal approximations. We're going to use these trig ratios and these decimal approximations to solve all kinds of problems involving right triangles. So we're going to need either a calculator here, or we're going to need a table. I'm going to talk about both. For the most part, we're going to be using the calculator, but the table is kind of cool. It's something that back before we had calculators, they could do these fancy calculations for us. You know, people would have books and books of these tables to have really high degree of accuracy for these trig ratios. Anyway, example 4, we're going to go ahead and use the table. We're going to be finding the trig ratios using our table. So you'll notice here, this is kind of like a one table just expanded. We have our angle measurements, 0 degrees, 1 degree, 2 degree, 3 degree, 4 degree, and so on. And then the corresponding trig ratios that are associated with that angle. So let's just pick a spot here. Let's just say a 4 degree angle. It's a small angle, but a 4 degree angle will have a sine ratio. The opposite side divided by the hypotenuse will be roughly equivalent to this decimal value, 0.0698. All of these are rounded to 4 decimal places. Otherwise, they may go on much longer than that. But that is the ratio of the opposite side divided by the hypotenuse whenever we have a 4 degree angle. The cosine value here is 0.9976. So the ratio of the adjacent divided by the hypotenuse would be roughly equivalent to that. And then this is the tangent ratio. Anyway, let's go ahead and take a look at these. I'm going to go through this first one, and then I'll give you a second to try the other ones real quick. So the cosine of 40 degrees. So we want to find a 40 degree angle here. We go through, okay, 40 degree angle is right here. The cosine ratio, that's our second one. The decimal approximation to 4 decimal places, because that's what our table is, of that is 0.766. 0.766. Now, technically, for 4 decimal places, there would be a 0 there. And this is a decimal approximation. This is pretty accurate. It's accurate out to the tenths, hundredths, thousandths, 10,000ths, so very accurate to the decimal place here. Generally, we don't want to round these numbers too much because we will lose accuracy. Depending on how accurate we want, we may end up using a longer approximation. So for instance, if I want to know a longer approximation of this, I can use my calculator to get this by pressing this value here. And you can see, yeah, if I cut it off at 4 decimal places, that's what our table gave us. But for certain problems, we may need or want to be more accurate than that. So we may need to use a longer decimal approximation. Generally, 4 decimal places is kind of the limit of like how much rounding you want to do, give or take. All right, next question, sine of 13, tangent of 27. Take a moment, pause, and try to find those in your table. I'm going to go ahead and get the answers here. So sine of 13 degrees right here, 0.225. Technically, there would be a 0 on that for 4 decimal places. And then the tangent of 27, so 27 degrees is here. Tangent is this one. So that's 0.5095. There we go. That's using this table. So again, they used to have really big, long books of these tables that would have even more measurements, right? Because 0 degree, 1 degree, that's accurate to 1 whole degree. But what if we wanted to know for like a 3.7 degree angle? Well, we would need more information than this table provides to us. So they would have books and books of this that engineers would use in order to calculate, more precise answers to their problems. So anyway, now we're going to talk about using the calculator. So we're going to go ahead and take our blue calculator. I mean, most scientific calculators have the ability to evaluate trig functions. Even, your basic cell phone has a calculator that can do this. But generally, a nicer one is going to make it a little bit better. So we're going to go ahead and figure out the cosine of 11 degrees. So you'll notice the buttons here for our trig functions, sin, cos, tan, sine, cosine, tangent. Basically what you do, cosine, and then the angle measurement. Now, it is important to note there are different ways of measuring angles, and so our calculators do have the option of being in what's called degree mode, where we have angles that are measured in degrees. You can see right here, this calculator says DEG up there. That means it is in degree mode. Other calculators will just have a D there sometimes as well. Or there's also a mode called radians, RAD. That's a different way of measuring angles. For the most part, we are going to be working with degrees in this class, so I want to make sure that that says degrees. Anyway, you hit the trig function that you're looking to use, and you don't mess up that. And then you can use parentheses like this, so cosine of 11, or you can actually just type in the number. We get the same value. Doesn't really matter. There are some specific details of where we maybe want to use parentheses if there's more than just the angle in there, if there's some like additional calculations, but it doesn't matter if you use parentheses or not for the most part. So anyway, we'll round that to 4 decimal places. So 0.9816. Right, that's our 4th decimal place, and then there's a 2. So we round it off there. 0.9816. And we can see that in the table as well. So 11 degrees cosine, it's exactly what we have in the table. All right, sine of 45. Okay, this is an important point here. Some calculators, including these blue graphing calculators that we have in class, have certain special angles, like a 45-degree angle. That's a pretty special angle. It's half of a 90-degree. Have certain exact values saved in them. So this is the exact value of the ratio of the opposite side to the hypotenuse of a 45-degree angle. If we want to know the decimal approximation, there's a button right here where it changes that fractional value into a decimal. If you press that, it'll give you that. There are a few others that will have certain exact values saved as well. So anyway, we have 0.7071. Again, we may need to use more decimal places than this. We may be okay using less, but not often. 4 is generally a good approximation for these. Final one, tangent of 2 degrees. So tan 2, press that button, and there we go. I'll go ahead and write that value out, 0.0349. And we can double check this on our table as well. So 2 degrees tangent. Yep, that's what we have. Sine of 45. 45 is down here, and sine is right there. It's the first one. Yep, right there. So for the most part, we will be using our calculators, but I thought it was useful to kind of examine this table and see where it used to exist. You know, it would literally be someone's job to sort of make these triangles and measure them accurately and then create these, you know, decimal approximations. Kind of cool. All right, so here is the big deal. Here is the big kahuna, the whole, you know, massive application purposes of this. We can solve for parts of right triangles differently than using your basic Pythagorean theorem or special right triangles or other stuff that we've learned up to this past. We can use these trig ratios to solve for sides, solve for angles, all kinds of stuff inside of right triangles. All we need are 2 pieces of information. We need 1 side and 1 angle, or 2 sides. In that way, we could solve for any part of the triangle that we want. We're going to start by looking at the sides here. So here, we have this angle right here, 15 degrees. This is going to be the angle that we use for this problem. And we're going to use it to figure out the length of x. X happens to be our hypotenuse in this case. And the side over here, the other one that we know is our opposite. Currently, we don't know the adjacent. For this particular problem, I won't actually be making use of it all. I don't know the adjacent, and I'm not looking for it, so I actually don't care about it in this case. Now, when we are using trigonometry, the trig functions, sine, cosine, and tangent, to solve for angles or sides or whatever we're doing, what I like to do is I like to know what parts do I know and what parts am I trying to figure out. That's going to help me decide which one do I use. Do I use sine? Do I use cosine? Do I use tangent? In this case, we know the opposite. So we want to incorporate that in some way. We want to use one of these two trig ratios that has opposite involved in it. And the one that we're looking for is the hypotenuse. So we want to use the trig function and the trig ratio that involves opposite and hypotenuse. That's sine, opposite over hypotenuse. So we're going to be setting up an equation. We're going to be setting an equation. It's going to be sine of our angle. Theta is a variable that we use in trigonometry to represent angles. So sine of our angle is equal to the opposite divided by the hypotenuse. This is the equation structure that we're going to have. We're going to plug in the values we know. So sine of our angle in this case is a 15-degree angle. So sine of 15 degrees is equal to the opposite side, which is 16, divided by the hypotenuse, which is x, our unknown. So this is an equation with a single variable. It only has x in it. Because, right, this is just some number. We could calculate it. We could go back up our table, look at it, right? 15 degrees, it's representing, approximately this value, 0.2588, whatever, Generally, I don't want to work with the decimal. I want to wait to round until the very end. So I'm going to keep this kind of nicely packaged up, and I'm going to just treat this like it's a number. Sine of 15 degrees is just a number. How do I solve for x? Well, I got to get that x out of the denominator. I have to remove it from the denominator. And the way that I'm going to do that is I'm going to multiply both sides by x. That will cancel it out on the right-hand side of my equation, and it will actually just move it on over to the other side because I have to multiply both sides by x. So here's what I have. I have x times the sine of 15 degrees is equal to 16. Hello. Sure, that's fine. So now to solve for x, I need to divide both sides by the sine of 15. Remember, the sine of 15 is just some number. It's 0.25 something. So we're dividing by the sine of 15, which again is just some number. Cancels it out, gets rid of it. I have to do it on both sides. So I have to divide it over here as well. This is going to leave me with an answer. I have to perform this calculation. I have to figure out what is 16 divided by the sine of 15. Fortunately enough, pretty much any calculator can do this. It's a little tricky to do on your phone, but it can be done. 16 divided by the sine of 15. This is all I'm doing here. This is one of those exact values. The sine of 15 degrees has an exact value stored in it. You got to be careful. Sometimes this happens. So you press that FD button, and we're going to work with this decimal approximation. So the approximate value of this is 61.81925, so on. We need to pick how accurate we want to be. Doesn't matter so much. I'm going to go with one decimal place, but there are cases, applications depending on, what purpose we're doing here, where we need to be more accurate, or we would even be okay with less accuracy. So the rounding is irrelevant. Just follow the directions, round to the appropriate level of accurateness. So 61.8 is going to be my answer. And there we go. We solve for the value of x, for the length of the hypotenuse here using trigonometry. Not too difficult, I think. This is kind of one of the two main setups that we're going to see. So whenever you have a trig equation like this, sine of an angle equals a ratio or cosine or tangent or whatever, if you're solving for a side, the unknown side is either going to be in the numerator or in the denominator, right? Those are the two options. In this case, it was in the denominator. That's actually the slightly harder version. If it's in the numerator, it's actually a little bit easier. So we're going to go ahead and take a look at a few more examples of this, and then I'll leave you to it. All right, so we're going to solve these some parts of these triangles here. We're going to go for it. So again, we need to know what trig function, what trig equation we're going to be using. So we look at what we have. We have this angle. Relative to that angle, we will label the sides of our triangle. So the side over here, this is our opposite. This side down here is our adjacent, and this side is the hypotenuse. So in this problem, we know the adjacent side, and we want to know the opposite side. Opposite and adjacent, those two sides are used in the tangent ratio. So tangent of our angle is equal to opposite over adjacent. This is the equation structure that we're going to be using to solve for this x here. We're going to go ahead and plug in the values that we know. So we know our angle measurement. So this is tangent of 24 degrees is equal to opposite, which is x, that's our unknown, divided by the adjacent, which is 12. Again, this is just a number. Rather than calculating it, rather than typing in tangent 24 and picking some rounding or writing out this long decimal, I'm just going to leave it as the tangent of 24 for as long as I can until I want an answer. And I need to solve for x. So actually, the only thing that I have to do, x is up in the numerator. This is slightly different than the one we just looked at. It's the kind of the other structure for these problems where the unknown is in the numerator. I have to get rid of this 12. That's it. And I'll just have x. So the way that I get rid of 12, the way I get rid of anything in the denominator like this is I multiply. Multiply by 12. It goes away. I have to do it on both sides, so I have to do it over here as well. And I end up with this. I end up with 12 times the tangent of 24 degrees is equal to x. I can calculate this. I can use my calculator. I can plug that in, and I can see what my answer is. 12 times tangent 24. There we go. We got the wrong answer because I typed in the wrong number. Was wondering why that was. Okay, here we go. Again, we have to pick where to round this, how accurate do we really want to be. I'm going to use one decimal place, but again, just make sure we follow any instructions that are given to us. So I'm going to call this 5.3. There we go. I'll go ahead and do one more example here. You will want to remember your sort of SOHCAHTOA to help remember which one you're picking, right? Opposite hypotenuse, opposite adjacent, adjacent hypotenuse, whatever. That tells you which trig equation to be using. All right, here we go. We have a 72-degree angle here. I'm going to go ahead and label the sides of this triangle. The opposite side is over here. This is our opposite. The adjacent side is down here. This is the adjacent. And then x is our hypotenuse. So we need to make a choice. What trig equation are we going to be using? What structure are we going to be using? Here we have a adjacent side. That's our known side. And the one we are looking for is the hypotenuse. So adjacent and hypotenuse tell us to use cosine. So that's what we use. Cosine of the angle is equal to adjacent over hypotenuse. That's the structure we're going to be using. So I'm going to set that equation up. Cosine 72 degrees equals 6 over x. And now we can solve. This is a lot like the first one, where the x is in the denominator. Multiply both sides by x. And now this is a number. I can treat it as such. I'm just going to divide both sides by that. There's my answer. Again, round it to wherever the instructions say. I'm doing one decimal place. Got several problems here down below that you can try now. See you later.